Our speaker for today is Professor Takashi Uemura. Dr. Uemura obtained his PhD at the Department of Polymer Chemistry, Kyoto University in 2002. He then began his academic career as assistant and then an associate professor at the Department of Synthetic Chemistry and Biological Chemistry in Kyoto University. In 2018, he moved to the University of Tokyo, where he holds the position of professor. He has received a number of awards, including Inoue Prize for Science, JSPS Prize, Cow Research Initiative Award, the Chemical Society of Japan Award for Young Chemists, and CSJ Award for Creative Works. He has been appointed as associate editor of several international journals such as Dalton Transactions, ChemLet, and Bulletin of Chemical Society of Japan. His research interest focuses on the preparation of synergistic nanohybrids between nanoporous compounds and polymeric materials, in particular, polymer chemistry in confined nanospace. Thank you so much, Professor Uemura, for joining us here today. The stage is all yours now.
Yes, thank you very much for your very kind introduction. So I'd like to share my slide right now. It's okay?
Yeah.
Can you see the screen?
Yes, please go ahead.
Thank you. Okay. Yeah, thanks so much. Thank you very much for the very kind introduction and invitation to this some kind of great online event. So it's a really nice opportunity to share research activity with many colleagues in the world, even though I'm in Japan, Tokyo. So I'm Takashi Uemura from the University of Tokyo. So I'm really happy to give a talk on this topic, meta-organic frameworks for advanced polymers. Okay, usually organic polymers are prepared in this type of macro-scale reaction vessels. Therefore, obtained polymers are always entangled like this, and it's quite difficult to control the polymer primary structures. However, if we can prepare an outside reaction vessels, and we can incorporate a monomer there, the poor wall would affect the polymerization so much, and control the polymerization with constant geometries would be possible in this system. So, of course, this type of polymerization has been already been reported using the organic host and the mesoporous silica system. However, in case of the organic host, it's difficult to apply these host methods for the variety of the polymerization system because of the narrow, fragile, and undesigned porous structures. And in case of the mesoporous materials, so the pore size is too large for the conventional monomers to control polymer primer structures. So what kind of nanosize of vessels are appropriate for our purpose? Here we focus on the metal frameworks, MOFs, so which are prepared by self-assembler metal ions and organic ligand like this. And as you know, these new porous materials, MOFs, are applied to the gas storage and separation materials usually. So here you can see the characteristics, features of the MOFs. Different from the diorite and the activated carbon. It's not difficult. It's rather easy to control the pore size or shape by changing the combination of these two components. Surface modification is also possible. High regularity because of the crystalline nature. And sometimes they show the flexible framework upon guest inclusion. So this means that we can design spaces with a variety of nano-size information. Here you can see our research interest. So we can program the nano-size information, such as dimensionality, pore size function, pore size and shape by changing a combination of these two components. And after the introduction of the monomers here in the MOFs and subsequent polymerization, so we can obtain the polymers reflecting the host structure information. So by using this technique, we can prepare the polymers with desired structures. Okay, so the first work with this type of MOF composed of zinc ion and BDC ligand. So because the size of this MOF channels, 1D channels, is suitable for incorporation of the only one or single conventional monomers such as the styrene monomers. So here let me show you the polymerization procedures. So how can we perform the polymerization? So the first MOF powder was immersed in the styrene liquid with AIBN as radical initiator to incorporate the monomer and initiated into the channels. And then after the evaporation of the excess amount of the styrene outside host crystal, we perform the polymerization at a higher temperature to obtain this polymer composite. And then for the characterization, so after the polymerization, so we check the SEM and found no change of the crystal size, morphology, and surface was observed after the polymerization. And then we also checked XRD and found that the porous frameworks maintained during the polymerization because the XRD pattern was not changed before and after the polymerization. Okay. So now we could obtain the polymer composite. But how can we isolate this polymer composite? How can we isolate the polymer from this composite? Here, yeah, it's very simple because this is a coordination compound. So yeah, here we just digest the framework by dissolution of the framework in the creating solution to give the polymer quantitatively. Then we checked the DPC and found that yes, this is really polymer with high molecular weight, and then polymer with high molecular weight, and also with the very low molecular weight distribution. So next, we checked the ESR and found that the propagation radical was very long arrived over 3 weeks, even at 70 degrees C. And the radical concentration was extremely high compared to the usual solution polymerization system. So this is because the propagation radical was protected in the channels, and a kind of the living radical polymerization proceeded in the channels. That's why we could attain the narrow molecular weight distribution shown here. Okay. So now we could obtain the polymers from this composite. So next, in this framework, we can control the pore size and shape by changing a ligand. And then we could perform the polymerization using these pores. So actually, stereoregularity of the resulting polymers can be finely controlled depending on the pore structures. And when we carry out the polymerization, of this type of the binary monomers, we could obtain linear polymers, remaining one binary group like this. So this type of polymerization has never been attained before, because to recognize these two binary groups is impossible in the previous polymerization. But this channel could direct the polymerization in the 1D fashion. Okay, so now we could perform the polymerization using MOFs. So what's next? So next target should be the sequence control to approach to the elegant biopolymer system. So as you may know, sequence control in copolymerization is very difficult for the synthetic polymers, usually giving random copolymers like this. So this type, so this is one of the most challenging topic in the current polymer chemistry. So sequence control is really difficult using in the conventional solution polymerization systems. Okay, let me show you our strategy to achieve the controlled copolymerization using MOFs. So as you already noticed, so MOFs have highly periodic structures because of the crystalline nature. So if we can immobilize a monomer periodically by chemical bonding at most, so we can introduce another monomer between them with regular interval, so that we perform the copolymerization between them to give the sequence-regulated copolymers shown here. So here we employ this type of the monomer, binary monomer, with the functional group. I mean the two carboxylic group here to mix with the kappa to give this MOF compound. So actually, in this system, periodic positioning of this styrene derivatives with a distance of the 6.8 angstrom can be achieved along the 1D channel. Then we introduced another monomer, acrylonitrile, between them to perform the host or guest polymerization, and found that so this is a predominant sequence. So I mean the AAAS repeating in the main chain. So here we could achieve the controlled polymerization. I mean we can transcribe the MOF periodicity into the polymer chain as the biological system is doing. Okay, so far I just talked about the control of the primary structure of the binary polymers. But as you know, so one of the biggest issues for polymer is chain entanglement. So actually, conventional one-dimensional polymers are chaotically entangled like this. So if we can restrict the growth and branching of the polymer chains two-dimensionally, so what kind of the topological effect is expected? So here we employ this type of pillar MOFs with an interior distance of the 8 angstrom. And then we carry out the polymerization of these styrene monomers with cross-linker together between these 2D layers. Then here we obtained this 2D network polystyrene in the very high efficiency. And then next, yes, we check the DLS because interestingly, this polymers, the obtained polystyrene, crossing the polystyrene was soluble, highly soluble in many solvent. even though they have a cross-linked structures. So next, we check the AFM and found the formation of the ultimately thin polymer sheets with only single molecular thickness. So this is the first synthesis using commodity polymers, such as the polymers, achieving the formation of the ultimately thin only single molecular thickness polymer sheet. Okay, so next we checked the viscoelastic properties and found that the stretch modulus of this 2D network was much lower than the 1D and 3D counterparts. And the loss factor was exceed 0 at a higher temperature, showing that the liquid-like behavior of this 2D network. So this is a quite interesting 2D topological effect because polymer chains are hardly entangled in this geometries, in these 2D geometries. Okay, here let me show you the video. As you can see here, this conventional 1D linear polymer shows the conventional elastic property. But this 2D network shows the flowing or melt behavior. So they show the quite different behavior in spite of the same constituent of the polysilane chains. Okay, so here, so far I just talk about the synthesis of the binary polymers using MOF, but actually we can prepare the many type of the advanced polymers using MOFs, including the conjugated polymers, I mean the conducting polymers, biorelated polymers, inert polymers, and even for the nanocarbons. So next, I'd like to talk about several topics focusing on this type of the nanocarbons, particularly for the GNRs, so graphene nanoribbons. So as you may know, GNR is a nano-sized stripe of the graphene, and they have been studied extensively studied for the application to the future electronics because they show the quite interesting electronic and magnetic properties depending on their width and edge geometries. I mean depending on these armature edge or zigzag edge structures. However, fabrication of the well-defined GNR has been mostly unrealized because of the synthetic problem. So here you can see the two conventional approach to the GNRs. So first one is a top-down method. So this method is really nice to make the GNRs in high scale. So scalability is very high, but precision synthesis is quite difficult. But in contrast, so bottom-up synthesis based on the oil synthesis or on-surface synthesis, so they can produce the DNRs with high precision, but scalability is not high. So we have to overcome this problem. But so if we use the MOFs, so they can achieve the scalable synthesis of the atomically precise GNR. Actually, when we perform the bulk polymerization of this type of the monomer. Graphic carbon is obtained with random cross-linked structures. But if we carry out these reactions in this MOF with high stability, high thermal stability in the 1D channel structures, we can align this monomer in this way to give the DNR with defined edge structures and with very high yield. So now we are trying to prepare the many types of the GNRs using the MOS. And one of the biggest challenges in this field should be to prepare the polyethylene at the narrowest graphene. So here, let me show you the history of long ascent synthesis. And the length of ascent has been slowly increased up to the 12 or 13 benzene rings over centuries. So formation of the polyethylene with numerous benzene rings is long sought after target and has yet to be realized so far because of the synthetic problem. So we tried to synthesize the polyethylene for the first time. So the first, here we perform the polymerization of this monomer in the 1D channel of this MOF. So actually, in case of the bulk synthesis or bulk polymerization of this monomer, so cross-linked and insoluble carbon was obtained here. But if we carry out this reaction in this 1D channels, we could obtain this polymeric hydroacid in good yield. Then we perform the characterization, and this solid-state NMR shows the formation of this precursor polymer. And this Martov spectroscopy shows the precursor polymer composed of several dozens of the linearly fused rings structures in this polymer structures. So now we could prepare the very long precursor polymers. Then next we just perform the transformation of this precursor polymers into the polyethylene just by heating. Then we checked the absorption spectroscopy. Absorption band expanded. We found the absorption band in the near IR region, showing the expansion of the pi conjugate system. And the NMR showed the signals for the only aromatic carbons. And IR showed the CH vibration bands for only solo, repeating groups, and quattro mode, the terminal groups, characteristics of the extended ascent. So now we're happy to say that we could obtain the polyascent, but here I'd like to remind you of the stability of ascent. So theoretically, polyascent should be very unstable because of the biological nature of the longer ascent, and actually even pentascent is unstable in the solution, easily oxidized or dimerized. So here we checked the ESR and the squid of the obtained polyascent and found that yes, the polyascent has biological nature in this system also. But actually, the spin concentration was considerably smaller than the expected. So this would be result from the intermolecular antihomogeneous interaction among the chains like this, as was suggested by the MD simulation and the XRPD patterns. Okay, so next we carried out the XPS and of this polyascent and found that the oxidation reaction took place only near the surface of the particles. So I mean the inside the particle is stable. So only the surface of the particle was oxidized like this. So this is probably because of the strong chain packing of the chains. So strong chain packing could inhibit further oxidation of the dimerization inside the chain, inside the particle. That's why the polyacid obtained here is stable even under the atmospheric conditions. So now let's check the length of the polyacid. The polyacid is insoluble in any solvent and cannot be volatile. So we couldn't estimate the length using the conventional methods such as the GPC and Markov mass spectroscopy, and also we can't use micrographies. But instead, we use IR because this is also the quantitative analytic techniques. So here we focus on the intensity of this solo and the quattro peaks because this is the repeating groups and this is terminal groups. And we found that the ascent length is linearly correlated with the relative peak area of these solo to quattro mode peaks. Then, so now we can estimate the average number of the benzene rings in the polyascents to be almost 19, which is overwhelmingly longer than the previous ascent systems. So this is a new record for the longest ascent, which will find many interesting applications. Okay, so so polymers. So polymers are giant and entangled. So they are quite different from the gas and solvent molecules. So these small molecules are easily adsorbed inside the MOF channels. But is it possible to adsorb the polymers directly into the MOFs? You may say no, because of the too large entropic loss to anchor. So polymer insertion into MOFs would hardly take place and seems kind of the crazy idea. But MOS can do it. So we could directly introduce the polyethylene glycol pegs just by heating above the melting temperature by melting process. So here you can see the simulation for the spontaneous permeation of the peg chains into the MOFs, which is an enthalpy-driven process with multiple van der Waals, CH-pi, and electrostatic interactions. Then actually, we can directly observe the polymer insertion phenomenon. So actually, that happened after the immersion of the MOF crystals into the neutral peg like this. So that happened only along the channel axis. So we could even insert ultra-long polymers with a molecular weight of the several millions, allowing for the formation of the morphography by the threading of the ultra-long polymer chains through the metal organic framework microcrystals. So we are really happy that this work was featured by many media in the world. Okay, so now we could understand that we can insert the polymer chains into the MOFs even though they are very long. What can I do using this interesting phenomenon? So here we focus on the terminal functional pegs because of many applications in the biology. So, however, the price of these pegs are very high, very expensive because the separation between modified and unmodified PEG is impossible. So we always have to perform the high conversion reaction to achieve to prepare the functionalized PEG efficiently. But, so this is a polymer reaction. So it's quite difficult to achieve the completely. So this means that the mixture of mono and non-functional pegs are often sold in the market, which is a really big problem for the biological applications. So we would like to overcome this problem, and then we try to separate these pegs with a different terminal groups. A modified one and totally modified one. So molecular weight of these two pegs is 20 kilodalton with so many same repeating group. But the same, completely same and very long repeating group with only terminal differences. So separation between these two pegs is impossible using the conventional size exclusion chromatography, SEC. But MOFs can do it. MOFs can recognize these two terminal groups. So actually, PEG-H, a modified one, can be inserted, but PEG-30 is not inserted because of the blockage by the large tortilla, like this. The actual separation of PEG mixture is possible. So we treated this PEG mixtures with more powder to capture the PEG-H only inside the pore. And after the washing with the dichloromethane, we could recover the PEG tortiles with high purity. Then next, we tested this system with other terminal groups and found that the insertion speed are strongly dependent on the terminal size. So we're happy that we could recognize the terminal difference here, but we carried out this experiment using the neat polymers, the melt polymers, so which may limit the further applications. So next question would be is it possible to introduce the polymers directly from the solution? Here we performed the solution adsorption experiment and found that, yes, with here the only simple PEG, so unmodified PEG. And actually, this PEG is adsorbed in MOF, depending on the solvent used. And more interesting things, or rather unexpected result, is that the larger PEG is more likely to be adsorbed because this is enthalpy-driven process. So we could develop this system much more. So recently, we have performed the MOF column chromatography after the packing of this MOF powders in the stationary phase. Then we injected the PEG solution and found that the larger PEGs eluted slower, which is completely opposite from the conventional SE systems. Because, as I shown before, larger PEG is more likely to be adsorbed in the MOS. So, of course, we performed the analysis of the other terminal functional pegs and found that the termini smaller than the pore show the retention, but the termini larger than the pore shows no retention or rejection. But if we look at these chromatogram more carefully, surprisingly, this Morphography can detect only marginal difference at the alkyl terminal, like hydrogen, methyl, ethyl, and the butyl. And moreover, the substitute position at the terminus will be finally recognized because this peg is rejected, but this is inserted in the nanochannels. So now we can say that we can recognize only single atomic differences in very long polymer chains. So as you know, polymers are mixtures. Mixtures is different chain lengths, composite, composition, and the structures. So even after the 100 years since the discovery of the polymers, separation and purification technology has made little progress, always rely on the separation by size or solubilities. But now we have polymer separation techniques using MOFs, so which is very useful techniques to obtain the desired polymers. So this means that we can create a variety of advanced polymers via separations using MOFs. So we call this technique as morphography, and our proposal got the first prize at the pitch contest of the Society of the Polymer Science Japan very recently. Okay, so then next let me show you the several examples of using the morphography. So as you know, the cyclic polymers show the very unique properties because of the no end groups. But general synthetic method for cyclic polymers include end coupling cyclizations. So this means that the crude product always contains unreacted precursors and chain extended linear byproducts. So there have been the strong demand for the efficient production method to give the cyclic polymers efficiently. So morphography can do it, can do the perfect discrimination between cyclic and linear polymers. Just simple temperature modulation like this. So at lower temperatures, linear peg is adsorbed strongly, but cyclic polymers are treated very quickly because this polymer is not adsorbed in the MOFs. We can scale up this system to the gram scale separations. So here we use the preparatory column with a large amount of the MOF powders. And after the injection of this mixture, so we could obtain 100 pure cyclic polymers. So showing that this method is highly promising to the practical applications. So, okay, as you know, in the central dogma, the genetic information of the DNA is completely recognized and transcribed in the enzyme, which is a key event in the biological system. But what about the artificial system and the synthetic polymers? So as I said, most can disentangle and stretch polymers. so which may allow the decoding of the polymer chains. Here we employ this MOF with a coordinated unsaturated site that can allow the accommodation of only coordination guests. So we try to introduce these these vinyl polymers with same shaped side chains with and without nitrogen atoms. Here, and nothing here. The next we check the XRD after the treatment with these polymers and found that the MOFs opened pores only for this polymer that can interact with the pore wall effectively. So biggest challenge is the sequence decoding of the copolymers. Here we introduce random copolymers with various monomer ratios and found that this more preferred the consecutive P array for the gate opening that can allow the strict recognition of the copolymers with only a few percent composition differences. Then we used block copolymers, which show the different gate opening thresholds between random and block copolymers. I mean, these block copolymers are more easily to be adsorbed. So all these results indicate that the MOFs can identify the monomer structures, composition, sequence, and the block architectures very effectively. So this means that molecular information in the polymers could be read out using the morphography technique. Okay, so now we can extend this system to the biological macromolecular separations. So here we perform the separation of fatty acid ether by morphography. And high precision separation with the recognition of the positional isomers is achieved. I mean, the cis and the trans isomer is recognized. So oligopeptide can be also analyzed. So morphography can become the very good tool for the peptide analysis. So much larger compound proteins can be also separated. So here we could achieve selective adsorption of the denatured protein because these proteins is adsorbed inside the pores. So here we could achieve selective adsorption of the denatured protein effectively, which gives a highly pure native proteins from the mixtures. Okay, as a summary, so rational design of the MOF nanospaces can allow not only precision synthesis of the polymer, but also the assembly and the selection of the polymers from the mixtures. So a number of the papers related to the MOFs and the polymers are greatly increased like this. So we believe that our methodology will contribute to the development of the MOF polymer hybrid research in future. All right, so before closing my talk, I'd like to thank my collaborators, particularly our staff and the students for their hard working. Okay, thank you for your kind attention, and I'm very happy to answer your questions.
Thank you so much, Dr. Imura, for this very insightful talk.